All right, clock's running, folks. Let's get to it. This is about, well, we've started our look at dynamic fluid or fluid dynamics with what we call the equation of continuity. And now we look at something called Bernoulli's equation, which really can, what's nice about it is it can capture everything we've done with static fluids. We certainly have to, in some cases, use continuity along with this equation, and it works for anything, any moving fluid, okay, any dynamic fluid. So let's look at some different cases. Now we're going to have a bunch of qualifiers here for Bernoulli's equation to work. The flow has to be steady, which means I don't know. Irrotational means that there's no swirling of the fluid as it does that. It just moves in straight lines. We already know what incompressible means. The density can't change. Non-viscous means the stuff's not thick and therefore it doesn't do something. Um, yeah. So, okay, a couple of cases. All right, case one here. We're going to look at what happens to this subsection of fluid here. And these are pressure gauges. Pressure gauge here, pressure gauge here. We want to look at what happens to pressure um, as fluids move in through different, constrictions or different sections of, in this case, like a pipe, all right, or an enclosure. So the big question here, I know your notes just say energy. Is energy conserved? Energy is always conserved. The real question is mechanical energy conserved? Well, here's what happens. We know from our look at continuity that in case one here, as this fluid enters this constriction, we're going to move to something more like this. There's that same volume of fluid. And here, if it has a speed v, here it has a different speed v, a faster speed v, because we know that A1 V1 is A2 V2. Well, you know, question one, is mechanical energy conserved? Well, I mean, mechanical energy is EPE and KE and GPE. There's no springs. This stays the same if we look at the center of mass of all the stuff. So that doesn't change, but KE does, right? It gets faster. So the answer is no. Mechanical energy is not conserved. All right. Um, so that must mean that there's some work done by non-conservative forces. We'll get to what those are in a couple of slides. Now, what it also means is if this thing speeds up, it means that there's a bigger force this way than there is this way. All right? That means that there's a bigger pressure here than there is here. And that means that the pressure here is like this, the pressure here like that. Fair enough? Okay, case two, is mechanical energy conserved? Well, now this, if we again just apply continuity, we still have the same exact area. So we have a velocity v there. We have the same volume of gas here with the same velocity. We'll say v1 equals v2 if this is 1 and 2. Well, forget about the EPE. We have KE and GPE. Well, KE doesn't change, but GPE does. We have a difference in height. So mechanical energy, again, not conserved. That means, again, that WNC is 0. Sorry, is not 0. Duh. All right, and again, what it means is to push this thing up the hill, we have to have a bigger pressure below than we do above. Right, and that's just, we've seen that even happens in static fluids, right? P below is P above plus rho GH. Okay, so far? Good. In a case like this, what happens to mechanical energy here, or really what happens to this, subsection of fluid? Well, it goes up the hill, and it gets and it gets faster. V. Continuity says it goes faster, and it goes up the hill. So here, GPE and KE both go up. So mechanical energy is like, no way is it conserved. And it means that the pressure down here is like a lot higher than the pressure is up here. Okay? So, in this case, again, we could say that WNC is not zero. There's work done by non-conservative forces. Well, why is that? It has to do with what we call the nature of fluid pressure. Well, this is something you talked about. You used the word gas last year. But why do gases exert pressure? Well, gases exert pressure on the walls of the containers that contain them because, I'll say that pressure is a result of the collisions that fluid particles, you said the word gas last year, is the result of collisions that fluid particles have with container walls. And I'll say, and the forces exerted during those collisions. Now, collisions. Yes, we talked about collisions in our last unit of energy and momentum. Here's some energy stuff, right? Well, what kinds of collisions are the ones that conserve energy? Well, they're only perfectly elastic. And these collisions are actually, here's a wall of a container. This is a fluid particle. It actually hits the wall and bounces off. This is called the kinetic theory of gas. We're using it for fluids in general. So these collisions are elastic, but not totally. So therefore, mechanical energy is not conserved. All right, that's a big deal. Big deal. All right, because these collisions, pressure is a result of collisions. The particles are banging into the walls of the container. They're actually contacting the wall, right? And those collisions, those types of interactions do not conserve mechanical energy. Okay? Okay. So, if we look at this real, this real small subsection, like we said, well, there's a bigger pressure here than there is here. All right, so I'll say that there's a P and there's a P, but then this has some more, a delta P. All right, now this subsection of fluid has area here that's the same area on both sides. Yeah. So that means that there's a force here, a force exerted on that side that we can call F. And there's a force exerted on this side due to the pressure that we'll call F. But this has some more force because of the extra pressure. And it's applied, let's say, through this distance d. So we can say that the work done by the non-conservative forces is F plus delta F. Well, sorry, excuse me. F net times D. And the net force is really just delta F, the difference in the two forces. Fair enough? Well, this is delta F is delta P times A. Pressure is force per unit area. Pressure, force is pressure times area. Yeah, times this D. What's that? It's that. Delta P times the volume, not velocity. Okay? So we can really say, I think we can, yeah, get into this this conservation of mechanical energy thing now and say that, well, WNC is delta ME, or is, let's say, GPE final minus GPE initial plus KE final minus KE initial. No springs, no EPEs. So I'm going to write this WNC like we did before as delta P times V. Well, this is, whoops, not 1/2. This is MGH final minus MGH initial, right? Talking about depths of fluids. Here, 1/2 MV final squared, V for velocity, speed of the gas, speed of the fluid, that is, minus 1/2 MV initial squared. Now, let's just, how about this? Let's turn this, well, I'm going to write this like this. Delta P, we're going to call P2 minus P1 times the volume. And I'm going to change this to MGH2, MGH1, MV2 squared, MV1 squared. All right, we'll just talk about two different locations, not the fluid before and the fluid after. Make sense? We're not talking about what state the fluid was in before and after any sort of event. We're just saying let's compare two different locations, literally in an enclosure. All right. Now, here's what this ends up being pretty cool. What we can end up doing is looking not so much at conservation of mechanical energy, but what we're going to do is do a conservation of energy per unit volume. We're going to divide everything by volume. And what we end up with here is P2 minus P1 equals, well, dig it. What is that? Mass per unit volume? It's rho GH2. Oh yeah, look. Pressure, rho GH, right? Same thing. We've seen that in our static fluid statement. Minus rho GH1 plus 1/2 rho V squared, right? Here's our mass per unit volume. Minus 1/2 rho M1 squared. All right, these are all, just so we're sure, energy per unit volume. So typically what we do is put all the ones on the same side and all the twos on the other. You can probably tell that, hang on. Okay, so what I did was I actually mixed up which pressure is which. What's that ding? What's this dinging? I don't know what that dinging was. So, and here's why, just so you know I'm not, what is that? What is this dinging? No dinging. So, does it just ding when I write? Yeah, that's so annoying. So annoying. Pausing. All right, let's see if that went away. So like I said, you know, if we look back at this last page, why don't I just go to it? You know, here is where the pressure is bigger, down here, bigger P, smaller P. So when we're here and we're saying that this is a positive number, right? We're saying that P1 is below, okay? And then notice I said that, you know, initial was 1. Well, initial is kind of like our below. All right, so just so we're sure that's, I'm not just making that up. All right, so here's 1, here's 2. So now we can put all the 1 stuff on one side and all the 2 stuff on the other, and we end up with this. P1 plus, that's a pressure, rho GH1 plus 1/2 rho V1 squared is P pressure 2 plus rho GH2 plus 1/2 rho V2 squared. This is called Bernoulli's I think that's how you spell it. Bernoulli's equation. It is a statement of conservation of mechanical energy per unit volume for any fluid. All right, notice what it includes. Right, it includes if things aren't moving. Well, sorry, I think that's in the next page. Yeah, well, good old static fluids. Sure, good old static fluids. Well, we can say that if this is like 1 and down here is 2, well, we can say pressure 1 plus rho GH1 plus 1/2 rho V1 squared is pressure 2 plus rho GH2 plus 1/2 rho V2 squared. Well, nothing's moving in here. It's a static fluid. Okay, so we can say that if we call this, say, height 0, and then we call this, I don't know, H, well, we can get rid of this, and we end up with pressure at 2 is pressure at 1 plus rho GH. Sure, right? That's our static fluid, our pressure at depth statement. Okay? So there's a nice application there. Another one, I don't know if this is a common one, but fluids moving horizontally. Here's a, you ever seen one of these, typically dump trucks have them on the back, a tarp, right? This is a truck that sells the tarp. It's a tarp company truck, advertising their tarps. A tarp is something that goes over, you know what a tarp is. Anyway, this truck is moving. Now up here, we have air that's moving fast. In here, we have air that's really not moving relative to the truck, right? The air in there, when you're in the back of the truck, it's not windy in there. You're standing on top of the truck, it's windy as all get out because the air relative to the truck is moving fast here. Well, if we look right along this boundary, we call the heights the same height, right? So if we say P1 plus rho GH1 plus 1/2 rho V1 squared is P2 plus rho GH2 plus 1/2 rho V2 squared. Let's call in here 1 and out here 2. Well, the heights are the same thing. Close enough to it. And let's say this is one of those open, next time you see a big dump truck on the road, you'll see there's probably a tarp either over the whole back of it or rolled up. Here's a dump truck. Looks like this. Cab part. Whoa. Wheel. It either has a tarp over it or there's a thing like this with a tarp like that so they can roll the thing over it like that. Dump truck. Fuel tank. Window. So there's a tarp over this thing, and, well, let's see. V1 is 0. The speed of the fluid, air, inside here, relative to the tarp, is 0. Out here, V2 is fast. And that means that pressure 1, is going to be pressure 2, air pressure, plus, I almost wrote rho GH, plus 1/2 rho V2 squared. So the pressure inside there is bigger than the pressure outside. And what does the tarp do? The tarp ends up bubbling up like this. Yeah? Sure. A classic, very standard example of Bernoulli's equation has to do with this. It says a jet of water, blah, blah, blah. We want to know what's the height of the water in the tank. Okay, now a couple of things. Oh yeah, of course, this turns into a horizontally launched projectile problem. Okay, but if we're looking for something about this fluid, it comes out here at a speed v, right? Let's name a couple of places. 1 and 2. 2's right at the hole. Okay, So we're going to find V. Well, let's see. No, I guess we know V, or we're going to have to find V based on this horizontally launched projectile stuff. So let's start there. All right, so we say, we go X and Y stuff. Let's see, delta Y is 1 meter downward. AY is G downward. V naught Y is 0. Delta X is 0.6 meters. We want to know what Vx is. Well, Vx is delta X over T. Only way to find T is to go over here. You should prove to yourself that the following is true. That's absolutely a mechanics exam type question. 2 divided by 9.8. So this thing is in the air for, this water spends 0.45 seconds in the air, which means, let's see, 0.6 divided by that, which means that Vx is 1.33 meters per second. Okay, now, if we go to this fluid thing, right, this is a moving fluid with 2 different heights and all that stuff, so we're going to do this. Whoops, we're going to use Bernoulli's equation, P1 plus rho GH1 plus 1/2 rho V1 squared, P2 plus rho GH2 plus 1/2 rho V2 squared. What can we get rid of? Well, let's get rid of H2. We're going to call this the bottom. H is 0. That goes. What else can we get rid of? Well, here's the dealio. One thing that you're going to have to assume, imagine, this has an area like that. This hole has an area like that. It's tiny. So we're going to say that A1 is way, way bigger than A2. You know, if the radius of that hole is a 50th of the radius of the top of the tank, then that means that the area is a 2500th of that other area, and therefore the speed is a 2500th up here than as it is down there. So, hang on, phone call. What we assume in this case, if this is true, we assume that V1, not V2, V1 is 0, okay? If it's a big, huge opening, especially compared to a little tiny opening, assume that this water level really does not drop that way with any what's the word? Non-negligible. I don't know. It's so slow we can assume it's 0, especially so slow compared to this speed. All right, so we get to get rid of V1. All right, the other thing is this. Here's another big one. If things are open to air, then pressure is atmospheric pressure, right? Certainly open to air here. This is a hole here. Open to the air. All right, so that means we get rid of both of these. They are the same thing. I'll say that P1 equals P2 equals P atmospheric. Okay? And look what we end up with. Rho GH1 is 1/2 rho V2 squared. Those go. And we get, well, that V is the square root of 2GH. Of course we do. Right? We're conserving energy per unit volume. So we end up with, you know, what we've come to recognize, I hope, from conservation of energy / kinematics. Okay? Oh, we're looking for the height. Sorry. Height is V squared over 2G. So squared divided by 19.6. What? Really? 9 centimeters? Hmm. Yeah, 9 centimeters. Seems like it should be higher than that. I guess we should try that. 1 meter up, it's going to go 60 centimeters out with a 9 centimeter high thing of water. Well, I guess this is pretty small, isn't it? Right? So, fair enough. But notice we didn't even use that. Okay? We didn't even have to use the diameter of the hole. I think they're just telling you it's pretty darn small, especially as compared to the opening at the top. Okay, so that's a super standard Bernoulli's equation application. All right, some water shooting out of a tank. This one here, this is a bit of a doozy. A doozy, I said it. And I want you to try this one. Okay? I do want you to try this one. Okay, but I'm going to help you out a little bit. Let's assume, this is the assumption I've made in the past. Shut up, dinging thing. Just deal with it. Assume that those measurements are to the center of this, what's called a venturi. All right, we'll talk about carburetor theory on Monday. Okay? Give this one a shot. Oh, now you block 1 people also have those continuity questions to do. All right, you got those continuity questions to do. I believe. Yeah, this is going to be a continuity part. All right, this is going to, at some point, involve this. Lots of, the dinging is driving me insane. Lots of Bernoulli's questions also involve continuity because notice we can relate V1 and V2. All right, folks, happy Thanksgiving. Or I should say, I hope you had a nice Thanksgiving, as I'm sure it's Sunday night now. And now you have a ton of work to do. Anyway, we'll see you soon, folks. 27 minutes, not bad. I'm a giver. Thanksgiving, I'm thankful for you. Bye.